So thank you very much, and thank you for having me. And unfortunately, this will be first talk that will break this beautiful stream of abstract interpretation talks. I'm always trying to convince my students, like, let's work on something exciting, but they usually come like, no, let's work on something, you know, like that is applications. So this talk will be applications and how to do modular verification and use synthesis in that. And I just find out that I don't have animations, so let me tell you what you would see here. I would start to talk about map function that you see here, and this is a simple function written in Haskell. Another thing that my students do to me, they come up with languages that they don't know and then write code in these languages. So we would have here a map that is just taking as an input a function of the type A to B, and takes as an input a list of the type A and returns an input a list of the type B. And if you look how this function is defined, it goes inductively more or less over the whole list. It just apply F to every element. And in this particular case, if you would call our liquid Haskell, this is joint work with my PhD student Bill Hallahan and Ranjit Jala and some other collaborators, you would actually get that this is the green dot. It will be easily verified. But if by accident we would forget this f of x and you would just have a function without f of x, then it wouldn't be able to verify. And now, you know, like you would assume, okay, I cannot verify it, so where's the bug? And if you call liquid Haskell, you would get something very unreadable. It would actually look like that. And what we did develop was actually symbolic execution engine for Haskell. So I'm not kind of telling you all the animation you have to imagine. And there in this, we would call our symbolic execution engine, which would tell you, look, here is the concrete counterexample to show you why this thing is not working. Now, if you would go to a next animation, which again we don't see, I really apologize for that. So what would happen was, I had another, you know, like this was all now explaining how things are working for the standard verification. And when we were developing this symbolic execution engine, we realized, well, it's nice to, you know, like we now understand well what were the problem with the Haskell. It has this lazy semantics, so all these things we could address. But one thing that we didn't know how to address was modularity. Because, you know, like as you have seen in the previous example, there was a simple counterexample that showed me okay, I had a bug, here is a counterexample, I could identify the bug. But here, in this particular example, we have a simple function which is called add2, and as the name suggests, it just adds a 2 to an input value. And if you look how we do that, this is the main function, and it has one callee function, which is increment. And when we call increment twice, it is actually doing exactly as what it should be. It increases the number for 1. That's also a thing that you're missing here in animation. But what is happening then, we cannot really prove that correct. And again, if you would call liquid Haskell, it would just kind of tell you something horrible because, you know, like we don't know what has happened. And the reason why this is the case, because when it comes to modular verification, the verifiers don't actually use the definition of the code, they just use the contract. And I don't want to just trash liquid Haskell because Ranjit is not here. If we tried the same in Daphne, it also didn't work, right? You see, if you look at the problem, you can see what is the problem. The contract for inker is not strong enough. It has to say not only that you know, like that it will be output will be greater than x, but it also has to say that it will be exactly input plus 1. And now if I ask you, okay, let's use symbolic execution, so what would be a counterexample? We don't really have here counterexample because both contracts are correct, nothing is violated, and yet we cannot prove. So for this purpose, now finally we see something in the green, we introduce something which we called abstract counterexamples. And this is if you look what this counterexample is saying, it says like, well, if I know that add 2 to 0 will be equal to 3, when I apply add 2 to 0 will be 3, if when I apply inker to 0 will be 2. And we can do that because, you know, like both of them are satisfying both of them are satisfying the spec. And now looking at that, once we introduce, this is our old work, these counter examples, then we actually hopefully, just a second. Okay, I think I don't have any more. Animation, so it will be much easier now. So once we have this counterexample, we can actually easier, if you're a user using symbolic execution engine, you can see, oh, I see there is a problem with inker. Let me go to see whether inker of 0 is indeed 2. And this is actually how the big picture looks like, right? You have a code, you have this specification, you call the verifier. If you didn't verify the code, that if you verified, everything is beautiful. If you didn't manage to verify, then you go and you will get either concrete counterexample, or in the case of modular code, you will get this chained abstract counterexample. So then we actually apply this to over, I think we had somehow almost 5,000 student exercises, and in almost 97% of the cases, we would correctly pinpoint, like, look, there is an issue here, you have to actually strengthen this code. And then we started to think, like, okay, we are now currently having user in the loop. We tell user, here is your spec is not strong enough. Could we actually do something about that so that we actually get, like instead of saying like, look, it shouldn't be just x is greater than 0, your post conditions, but it should be instead like x is equal y plus 1. We actually then said like, okay, let's actually put user out of the loop and try to do all this automatically. So this is now how the big picture looks like of our current work. So, like instead of just kind of reporting user, here is probably some issue, like we also say, we try to close this loop. We create both from concrete in abstract counterexamples, we create constraints. We take these constraints, we add them to synthesizer, and then the synthesizer is trying to synthesize spec, which is actually then pulling back in the program, and if you manage to verify, great. If not, you will get another sequence of counterexamples, and you repeat that loop. So this is the big picture, and now I won't have time to go through all the details, but I will leave the slides, and if someone would like to see all the math behind it, I will gladly explain later on. But now I will explain you what are we doing just on this example. So I need to still repeat, because somehow almost like I had the vision that we will need counterexamples to see. When in this particular case, where I forgot to add f of x in the beginning of the map, here is what you see is the concrete counterexample, which tells you, look, applying map to identity function and the list containing only 1, you will get 0. So this is concrete counterexample. And then we call those things abstract counterexamples, which probably is wrong, the name, because we should have called them counterfactual counterexample, looking now back. But what we dare say is like, look, again, on this particular example is like, counterexample will say, if inker of 0 is 2, then add 2 of 0 will be 3. So we kind of give this chaining thing. Now let's, as I said, like I want to now show on the simple example, how do we actually infer this spec? And I have here one function, it's concat, and if you look what is it doing, it takes as an input a list of the list. So when you see double brackets, that's list of the type A, and more or less it flattens this list. So like you have list of the list, and you just want to get a simple list containing all the elements. And if you look at the definition, it's doing it inductively. So it takes first two lists, appends them into one list, so it's calling the function app, and then after that it just continues inductively. So now looking at that code that you see here, you will say, okay, can we verify that code? And you can immediately say that you can't verify this code because there is absolutely nothing that we know about function or function app, right? We just see that there is this app. And if you look up there, I didn't define what is sum size, but because concat has a spec, but this is as natural as it is defined on the side. So it is just, like you say, the resulting list of concat should have the size of that list should be sum of all sizes of the lists that are in there. So now let's assume we try to verify that, and the first thing that we will get first counterexample, which will which will tell us that if app of 2 empty list is a list containing 0, then concat will actually, then the post conditions of the concat will be violated. So this is our first abstract counter example. Then we want to see, okay, let's see what is actually app of zeros of 2 empty lists. And when we evaluate this on the real evaluation, we will get, well, this is just an empty list. So then we will derive synthesis constraints, which will tell us, we will talk about preconditions and postconditions, saying like, if I have to, in both of cases we say like first for abstract counter example, which says like, well, if I have 2 empty lists and their preconditions are holding on them, then definitely we know that postconditions cannot hold on them and the list containing 0. But postconditions definitely have to hold on them and the list containing and the empty list. Once we have that, we continue and we try to synthesize, we give this to our synthesizer and it produces the first spec. The spec will just say, well, based on these constraints that you have, maybe the output is always the list of the size 0. Now what we try to say, that's already some spec, probably better than nothing, except that this is wrong spec, as you can see. So what we try to do next, we actually try to verify that this is correct spec for the app, but in that case, we will immediately find a concrete counter example, which will say, well, running app on the 2 lists, one is containing only 0 and the other one is empty, we will get a list containing only 0. So by having that, we add another constraint to our already previously existing constraints, and we derive another synthesis constraints. We continue the process. We try to synthesize something else. Maybe now we will get a new spec, which is still not correct, but it's getting somehow better. And then we will get another concrete counter example. And we continue the process until we reach the correct synthesis, correct spec for the app function. And with this correct spec, we can actually formally verify the concat function as it is. So that's just kind of outlining on this example. There are many details that I'm kind of hiding from you. It looks that there is only one type of abstract counter examples, which is not really true, because we think we have around 5 of them, depending whether the preconditions is violated, whether the postcondition is violated, whether we need to go backtracking. But before I go to backtracking, let me actually say how this actually works. So if you look at this picture, right, we have concat and we had app. So we can have a callee and caller function, but we don't need to necessarily have only 2 functions. In our biggest evaluation example, we had 34 functions, one being calling the other, so it works well for the whole libraries. And if you look at the big picture, how we are trying to do that, we assume that there is a spec only given on the top level, right? The top level function has to have a spec because we try to verify. And then what we go level by level. So we come here, we say like, okay, now I'm a caller, who are my callee functions? And then we are trying to verify callee functions so that they have a strong enough spec so that we can actually verify the function that is calling them. And we just continue level by level down. So you might actually assume, well, is this as straightforward as it is until you reach the leaf nodes? I already said no, sometimes we also need to backtrack. And there are several reasons why we have to backtrack. As I said, what I'm hiding is also all sorts of counterexamples, abstract counterexamples that we have. But what we also have to do is there is very often a chance that was when we kind of realized we were pointlessly running in the loop, was that what happened is for us, we call CVC4. It kind of keeps we actually have our own, we would keep getting the same counterexamples and the same counterexamples over again. So you would keep deriving very similar spec that wasn't really useful. So what we were doing at the end was we were just running, deriving the same spec. So what we had to do when we realized that this is happening, to prevent this, we would also from the counterexamples that we have derive, if needed, interpolants to prevent this same thing from happening all over again, because we needed this for the proving the determination for certain logic soundness and completeness. So that's, like more or less, we start on the top and we go to the bottom, and all this is done automatically. User doesn't need to provide any feedback. So if user provides some sorts of specification in between, nice, it can sometimes help us to derive things faster, but otherwise we derive all the spec as you have seen on the example that is here. I wanted to talk more about linear integer arithmetic, but I see that you're 2 minutes. Okay, perfect. So then, linear integer arithmetic. Now we are talking my true love. I mean, when I was doing my PhD and everything, decision procedure for linear integer arithmetic, that was the thing that I like. So when we looked into linear integer arithmetic and synthesis for linear integer arithmetic, we realized it's not only the things that you see, that you would get things like, oh, I have input that is negative and I want output that is positive. There are two other things that would appear. Like, for example, things that were, that were integers, but were not really integers, like measures. That is a feature of this liquid Haskell, which is kind of also there to ensure somewhat termination. And we would be able to say things, or the measures, like in the sense that we would say, you have seen measures, like, look, size of the x is great. I have a list that will be greater than 0. Of the sum of all sizes has to be greater than 0. Or also content, right? You will say, I want to create a list of all elements that are greater than 0. So what I thought was a really neat and it's a kind of a cute trick. What we did was actually, like, imagine we have here function f, and if we are dealing with if we will have to deal with the sizes, and like you derive that post has to hold for, let's say, a list containing 4 and 5. Now, if I have to deal with the sizes, what was the trick? As I said, like, it's not a big deal, but it's cute. We would say, okay, let's compute what is the size of the list, because maybe we will need to deal with sizes. It's 2. So we put there 2 with special comment, like, remember that this is actually a size and not just any integer variable. And then when we would do that, we would actually, when we would derive property, maybe that the post says that this last thing has to be greater than 0, we would remember, oh, it's a size, so then we would insert it back. I mean, as I said, like, it's a small, cute trick, not a big deal. And a similar thing we also did with the content. So if we needed to deal with the content, we would have additional part that I said, like, many things I'm kind of hiding here that would talk about post about the content. And then you can see the first part has this 2, which is actually size. And the second part talks really about the content. And then when we would try to synthesize post for both a list and the content, we could actually see, maybe we derived that content elements always have to be greater than 2, or the list size always has to be greater than 0. So then when we would convert this back to the spec, we would say, and the output is the list of the elements which are all greater than 2, and the size has to be strictly greater than 0. So let me just go to conclusions. I mean, we did evaluate, really, indeed we did. And I want to just say, I'm really proud of the fact that we had 34 different functions, and it was k-means function. Spec was only on the top level, and we managed, to call this under 10 minutes. We managed to actually fully synthesize it. And maybe when I show you just on this simple example, like with x+1 or append, it doesn't look impressive. But when you have a bunch of the functions, and like each of these functions can actually have so many options. So all the optimizations that we have to insert, and having it done under 10 minutes, I think Bill did a really good job. I wanted to, to conclude, so when it comes to modular verification, there is one thing that we learn. It's very important that we somehow understand that some standard tricks that we knew, like how standard counterexamples do not work there. But once we introduced those counterfactuals that were kind of explain if something goes wrong, what else will go wrong, we were actually able to do this and then synthesize quite a lot of spec automatically. I mean, it's still not ideal. It is a work in progress, but it actually being evaluated on the real programs that were written by PhD students using Haskell, and being able to help them was actually showed that I think in the first evaluation was that when we tried to pinpoint the bug, which actually where they didn't have a strong evaluation, that was really very successful, 97% of the cases. And here we were actually able not even pinpoint but automatically synthesize. So thank you for your time.
Yes.
So if you have a caller and a callee, and you're trying to synthesize the specification of the callee in the context that it should respect the specification of the caller, you have the choice about many possible specifications in general. Does your algorithm converge to the weakest, to the strongest, to something in the middle?
So let me recall, we actually, so when it comes to, you see, when I said there is also lots of backtracking, right? So practically we take the one that CVC4 returns to us. So it's, and we somehow also, in order to make it scale, we do iteratively. Like we put the bound of the size that can be derived. So it's, like not like logically tightest, but, like size-wise tightest, but then we continue, like if in case that the one that you derive here in the middle was not strong enough, and that means there was some problem below, so that's why I say we don't go back, because that's, like we will find that there is need to strengthen or relax it. Yeah.
Patrick?
I have a similar question, because in your iteration, you compute a fixed point of a function that may not be increasing if the program and the specification are contrary, they are contradictory, and so you may iterate forever. You have no guarantee of...
No, we won't.
Or you do some, what I saw interpolation, which is a dual narrowing, and so this does not guarantee... you always guarantee some program specification, but it could be the program that does nothing.
Yes, that's correct, but it depends really for the logic that, like, this is not like for, like we cannot claim that this will always work and always terminate, but we can go for example, for linear integer arithmetic, we have these guarantees, and I guess we have these requirements that if we, it's somehow almost like cheating, saying like if there is finite number of solutions, that we will definitely find them, which is, like not really, this is definitely, I agree, it's a cheating, but for linear integer arithmetic, we go in this iterative way, and then we actually show that up to size k, we will find a solution.
But you can have a non-terminating program with where the contradiction is unbounded. And so I don't see how you converge in this case. Maybe you require termination of the program and you're bound in the number of steps.
Just a second. So we do terminate. It is true that that is possible that we won't always terminate. That's I agree, because we don't, but for certain logic, we do have guarantees, and in practice, it worked well. But that is, like it is. Yes, no, I agree with you. I mean, that it is. As I said, like it really depends from the logic in which the spec is expressed. For for certain logics, we kind of showed for linear integer arithmetic. For others, we didn't even. Yeah. Thank you. Yeah.
Okay. Dino?
Yeah, maybe my question is related to the one by Patrick. I was wondering, once you get the synthesized constraints, are you checking somehow the consistency with the original constraints? with the regional specification? Because it seems that you just pass it to the verifier without double checking the fact that you are inferring something which is consistent.
It is going both ways, so right? When I derive spec for a certain Collie function, remember it is bounded with the fact that the spec has to help us for the Collie function that we prove and verify the caller function. So this is check, but also we check when we derive spec, if it corresponds. So, it's just a spec that we found, and then if it turns out somewhere lower that this was not strong enough, then we will get more constraints.
Okay, thank you.
Yeah.
Okay, thank you.